Hi, welcome to the second part about data processing. So previously we have discussed standalone processing, which was operating on a single node, and this time we will see how to do the opposite, so how to do the data processing at scale on different nodes composing a data processing cluster. So the key part for this talk is that if you cannot process your data set because it's too big to be fit into a single machine, then you have no choice. You must use the distributed data processing. So once again, you should choose your weapon for to each problem apart, because as I said previously, if the data set is small, the overhead of distributing it can be less efficient than processing in a single node. But on the other hand, if even technically it would be somehow possible to process a big data set, for example, of hundreds of gigabytes in a single machine, then doing that it will probably be less efficient than scaling and doing it on a distributed data processing on a distributed data processing cluster. So keeping this in mind and always choose the solution, the data processing solution, accordingly to the data set you are facing and you have to process. So what this distributed data processing is? We can imagine an example of files because it's quite easy to illustrate. So we have a big data input data store. So we call big data because there is much more data that could be processed in a single machine. Next to it, we have a cluster of 4 nodes. These nodes are called workers because they are doing the data processing work. And in the end, we have our big data output data store, data sink, and it's a data warehouse for this example. And among the examples of the distributed data processing frameworks, I have already mentioned them in the Who Data Engineer Is lesson. But anyway, let me just recall that we have Apache Spark, Apache Flink, and Apache Beam via Google Cloud Dataflow, because remember, Apache Beam is just an API that can be plugged on different runtime backends. So just to recall some context, we have 4 files that we are want to process separately on different nodes. So spoiler alert, you will see that even though we have 4 nodes and 4 files, it doesn't mean that each file will be processed in a single node. Why? Simply because you can already see that the files have different size. So if you don't balance the work correctly, then one worker will have much more work to do than the others, and probably this worker will define the data processing time of your job. Here we would like to have a more balanced distribution so that we can have a shorter running data job. So how to do that? We defined a threshold of 10 gigabytes per worker, and now the distributed data processing framework will analyze the data source and distribute each file or only a part of the file to a worker. So it looks like that. We have file 1 which 10 gigabytes going to worker 1 and 2 gigabytes going to worker 2. We have the file 2 completely going to the worker 2, and we have 3 gigabytes of file 3 going to the worker 2. So even though this file processes this worker processes 3 different files, you can already see that the volume of data to process is the same than for the worker 1, which processes only 1 file. And to follow the example, we have the remaining part of file 3 and file 4 going to worker number 4. And so processed data is later written in parallel. It's quite important to notice parallel, so that the execution job will be much more efficient. So we've written it parallel to our output table. And it's also important not only to know about this distributed data division, but also about some key terms that you will encounter in learning a distributed data processing framework like Apache Spark or Apache Flink. So the first one is partitioning. So that's something we saw previously in the previous slide. So the partitioning is how the distributed data processing divides the data source in order to process it efficiently and without any unbalanced tasks that are called also data skew. So in our example, you saw that we had one file going to the worker 1, one file to the worker 1, and later 3 different files, but very small chunks really, going to worker 2, the whole file, the remaining part of file 3 going to worker 3, and the rest parts to the last worker. So I put that this partitioning is calculated because it's you who define the 10 gigabytes per partition. But you will see next that it's also something natively provided by several data sources. So here we have a distributed data processing example, reading data from a streaming broker. So streaming broker is often composed of multiple partitions composing a much more global entity like a topic. It can have different names. In fact, in Apache Kafka it will be a topic, but in Kinesis data streams, for example, on AWS, it will be a stream. But anyway, here the partitioning is native, and distributed data processing framework knows this topology, knows that there are 3 partitions in our case, and it can associate each partition to a corresponding task worker. So that was for the data source distribution. But now what to do if your job is on a static cluster and you know that maybe next week you are going to process twice much data as you are processing right now. So when it happens, you have to think about scaling your workload. And the first scaling strategy is called vertical. So the idea here is that you add more compute power to each worker. So for example, you increase the number of processors, you increase the memory, or maybe you plug a better network card to optimize the throughput. And all this can contribute in processing the increased amount of data much more efficiently. But it's not the single strategy, and by the way, it's not the strategy that was popularized with MapReduce almost 20 years ago, because MapReduce talked about processing data in commodity hardware machines, so not necessarily something very compute expensive, because the idea was to plug multiple smaller machines to process big data sets. And this plugging, this interconnection of small commodity machines is called vertical scaling. So here, in order to have a better throughput, in order to process much more data in our job, we are going to add much more workers. So here you can see that we have 4 workers, but now we added 2 extra ones, and these arrows that are quite huge here are much more smaller in this part, because thanks to these extra workers, we were able to divide even more the input dataset, this huge dataset that we are going to process. And that was for making your job adapted to the data source. And now it's time to see much more compute related operations. So the first operation is called shuffle. So that's quite interesting, because you can imagine that we have different figures as on our screen, and these figures come from files. So each worker read some files, and the resulting figures are coming from these files. And now how to count each number of figures, how to do that. It's a really very complicated task, because you can see that each worker have some figures of the same type. So here you have 2 workers with this figure. Here we have, even each worker has this figure, and only 1 worker has a circle. But anyway, yeah, if you do the count separately, you will not get the good result. And that's when the shuffle comes in. So the idea of the shuffle is to bring all data of the same type to the same worker. So here we are going to decide that this figure goes to the worker 1, and this figure goes to the worker 2, And in the end, it gives something like that. And not only now that you can generate the count. So in a nutshell, shuffle is like moving data across the network in order to bring the related rows together to do some computation. So if you know SQL, it's like doing the group by at scale with different nodes storing the whole data set. But what to do if one of your tasks fails? So on the screen you can see that we have 4 tasks, and it's kind of a directed acyclic graph, because job first creates the first task. We can imagine that this task contains the reading part of the files, and later we have the second task that maybe contains some filtering logic that we are going to write in the end. So now when one of the tasks fails, we can see that task 2 completely fails, that maybe the worker is down, it might have some memory issues. And what a distributed data processing framework will do is that it will simply detect that fact through a resource manager and schedule this failing task. So from the beginning, from the files reading, because since there is this information of the compute graph, it's very easy to do. So the data processing framework will simply schedule this task on different node. And of course it has some implications like slower data execution time, but yeah, still data job will be slower, but you will get your result in the end, and it's maybe something that you prefer over very short execution time, which obviously if the task fails and doesn't have this fault tolerance mechanism will never happen. And now let's see some much more precise example of shuffle, but in the context of the MapReduce framework. So here we are going to see 2 steps of MapReduce framework, map and reduce. And to do that, we are going to answer the question, how many even numbers we have in this data set. So now we are going to start the first step, which is the mapping. And in the mapping, we are going to apply a filter method called isEven to detect whether the number is even or odd. And if it's even, we are going to keep it in the worker memories. Otherwise, we'll simply discard it because we don't need it. And after that, we are going to do a local count. So it's something different than previously in the shuffle example. That was quite simplified vision. Here is much more precise. It's something that is more realistic and something that happens on distributed data processing frameworks. So the count is first local to each worker. So you can see that we have 3 items in the worker 1, 1 item in worker 2, and 2 items in worker 3. And all this is the map step because it happens inside one worker and it works on the input data without necessarily exchanging it across the network via shuffle. And now we are going to generate the final result, which is the total count of items, and we are going to do with the shuffling, and this shuffling will give us the number 6. And this step of taking data from each worker is called reduce because, as the name indicates, it reduces the disparate data results into a single item that is required by the program. And about the architecture, so the architecture is distributed, so where we have some different nodes. Again, it may be different depending on the framework or the service used, but anyway, we can distinguish something like driver, which is kind of master or main controller of the workflow. So it will do the communication with the cluster. It will also, with cluster manager, it will also do some scheduling and stuff like that. And we also have workers that will be more responsible for doing the job of processing data by getting the instructions from the driver. But something which is quite important is that the communication is bidirectional. So the driver communicates with the worker, but the worker can also must answer back driver to its request. And additionally, the worker can also initiate the communication by saying, hey, I cannot process this data right now. Maybe you can try to schedule it somewhere else. In addition, there is also communication between the workers, because it might be more efficient to, if you want to maybe exchange some data that was once sent by the driver, it may be more efficient to exchange it from worker 2 to worker 2, worker 1 to worker 2, sorry, and later you have already two workers that can have this data, and other workers can fetch it directly from them instead of overloading the driver communication. So there are different things, as I said, the messages, like for example for remote procedure calls, like for example scheduling of different tasks, and maybe also the distribution of binaries, because the archives or the packages of your jobs will be sent to the driver and later also distributed to the workers, so that they have the same code. And additionally, if you define some code locally on the driver, the distributed data processing function may decide to serialize it and distribute to the workers, so that they have this too, and they can do the processing correctly. And yeah, there is also some communication where one worker can go down, and the whole cluster must be aware of that. And that's generally all. It was maybe the most technical lesson. I tried to summarize it as best as I could, but believe me, doing distributed processing is not as easy as it looks like on the schemas, and I hope that you will see that later in this course. And yeah, hope you enjoyed the lesson, and see you in the next one. Thanks for watching.